Professor Loeb wasn't finished. He went on to talk about a Manhattan-sized interstellar object. He's been on the show talking about it a lot. It's called 3I Atlas. It's currently making its way through our solar system, and we've been tracking its progress very closely, especially because Professor Loeb suspects that it might actually be alien technology scoping us out.
There's a surge of adrenaline in the astronomical community as the 3I Atlas, already a rare interstellar visitor, undergoes unexpected shifts in its trajectory, prompting signs that it could be speeding toward the inner reaches of our solar system in a way no one fully predicted. The James Webb Space Telescope JWS and its fellow observatories are racing to track every flicker of change, every hint of gas and dust, every deviation in the path of this enigmatic traveler from beyond our sun's domain. This is not just another comet passing through. It may be offering a once-in-many-lifetimes chance to witness the dynamics of an object born in another star system and now threading its way through ours, perhaps with a twist. Before we start, smash the like and subscribe buttons for more updates. From the moment 3I Atlas was discovered, it was unmistakably different. It entered our solar system at a tremendous velocity, not bound to the sun in the way comets native to our system are. As such, it was classified as interstellar. The JWS tasked its powerful instruments to study 3I Atlas's composition, structure, and behavior, aiming to uncover clues about where it came from and how it has remained intact over what could be billions of years of cosmic travel. Initial analyses revealed an object rich in carbon dioxide and other unusual volatiles. Unlike the typical water-dominated comets we know, the twist comes in the trajectory. While earlier models spoke of 3I Atlas swinging through the solar system and emerging again into interstellar space, more recent observations suggest its course is shifting in unexpected ways, possibly nudged by solar heating, jet outgassing, or some additional force yet to be fully understood. The fundamental implication is that this object may be turning a corner, heading deeper into the inner solar system, and perhaps toward the neighborhood of Earth's orbit, or at least crossing paths that bring it startlingly close in cosmic terms. What makes this remarkable is the sheer rarity. Interstellar objects are not everyday phenomena. Until now, only a handful have been identified. Each one offers a fresh window into the materials, and perhaps the processes, that shaped not just our solar system, but countless others. And this is the very reason why 3I Atlas is so eagerly watched. The JWS observations, combined with ground-based data and instruments aboard probes, are helping build a picture of an object that may predate our sun by billions of years, carry within it a record of alien star system conditions, and now, under the glare of our sun, begin to change in ways that make it profoundly relevant to us. One core implication of this shifting trajectory is the reconsideration of how interstellar objects behave when they pass near a star like ours. For decades, scientists assumed that these visitors would fly through predictably, slung in by gravity, shaped by their original systems, and largely unaltered by their transit through our neighborhood. What 3I Atlas is teaching us is different. As it comes closer to the sun, solar radiation is heating it, sublimating its ices, releasing plumes of gases like carbon dioxide, water vapor, carbon monoxide, and others. This outgassing can act almost like a rocket, nudging the object's path ever so slightly, causing its trajectory to evolve. JWS's data revealed a CO2-dominated coma, the mixture of gases being released, as having a ratio far higher than typical comets. This suggests not only its extragalactic heritage, but also that its path through the solar system cannot be assumed static. From a celestial mechanics perspective, this means we must treat interstellar objects like 3I Atlas, not as inert rocks drifting by, but as dynamic bodies capable of changing course in response to external forces. The sun's gravity is only part of the story. Solar heating, jetting, perhaps tidal stresses as they pass close to a star, might play significant roles. If any of that leads to a shift in trajectory that brings the object closer to Earth's orbit or intersects with planetary paths, then the stakes of such monitoring become even more pronounced. In terms of planetary defense and what it means for Earth, the possibility that something from outside the solar system could reach or near Earth is both alarming and fascinating. Traditionally, we focus on asteroids and comets originating within our solar system, objects we've cataloged, tracked, predicted. But an interstellar object by its nature is coming from beyond our gravitational dominion, often at high speed, on a trajectory that we might only learn about once the object is already within millions of kilometers. If 3I Atlas is indeed altering its path toward the inner solar system, the window for tracking and response is narrower, the uncertainties greater. It challenges our current monitoring frameworks. Are they sufficient for objects whose origin, structure, and behavior likely differ from the ones we know? Moreover, the implications for planetary science are profound. What 3I Atlas carries with it is a sample, an unplanned, though somewhat accidental sample of alien material. The fact that we have instruments like JWST observing it as it approaches means we can gather compositional and structural data in real time. If, for instance, it brings to the inner solar system material that has never experienced the conditions that objects native to ours have, no heavy irradiation from the sun, no strong tidal or planetary interactions until now, then what we observe could tell us about the chemical pathways and physical processes in alien systems. The high CO2 ratio, the deep irradiation crust suggested in studies for comparable objects, underscores how differently things may form and evolve in other systems. Its trajectory change also gives a unique opportunity to observe how an interstellar object responds to our sun's influence. As it moves toward perihelion, its closest approach to the sun, solar heating will accelerate the sublimation of volatile ices, increasing outgassing, driving dust and gas jets, possibly shedding mass and changing velocity. These changes are also potentially predictive of fragmentation or rapid morphological change. With careful observation, we might watch 3I Atlas morph in front of us, altering its shape, shedding new material, its tail and coma evolving. The fact that it may be heading in our general direction amplifies this opportunity to study it from within our inner solar system vantage. From a broader cosmic context, if an object from another star system can enter our solar system, change course under our sun's influence, and head closer toward Earth, then many things follow. The concept of solar systems being relatively isolated starts to look less absolute. The Milky Way might be richer in interstellar interlopers than imagined, meaning Earth and our solar system might be subject to visits, possibly rare but not impossible, from truly alien material. Each of these may carry unique chemical signatures, possibly life precursor compounds, or even structural features we haven't considered. 3I Atlas thus becomes a threshold moment in how we think about solar system boundaries. When we talk about the risk, it's not alarmism, but acknowledgement of an expanding parameter space. Objects like 3I Atlas may not be large threats in the way near-Earth asteroids are, but their speed, unfamiliar composition, and unpredictable paths mean they require a different kind of awareness. If our detection systems are tuned only for solar system native objects, then we may miss or mischaracterize an interstellar object until it is already too close. That makes the trajectory changes of 3I Atlas all the more important. They remind us how quickly the unexpected can arrive. The scientific community is also rethinking models of comet evolution, solar system dynamics, and even planetary formation in light of what 3I Atlas shows. For instance, the idea that comets from other systems might seed planet-forming disks with material is gaining traction. Studies suggest interstellar objects could deliver solid mass across star systems, contributing to planet growth in young disks. If 3I Atlas, or its kin, can enter another system, interact gravitationally, and deposit material or even modify orbits of smaller bodies, then the classical view of each solar system as closed and isolated becomes less valid. But of course, the human fascination is as much in the what if as in the what is. What if 3I Atlas does in fact come closer than predicted? What if its jetting alters its path such that it intersects the orbit of Earth relatively unexpectedly? The mere thought elevates the observation of this object beyond routine astronomical curiosity into a scenario where millions of eyes across Earth's observational networks and space missions are watching, calculating, modeling, and preparing. It is a reminder that cosmic surprises do not adhere neatly to our schedules or our best prepared models. There's also an invitation here for humankind's exploratory instinct. Should we ever in the future develop the capacity to intercept such interstellar objects, study them up close, or perhaps even sample them? 3I Atlas is teaching us what instruments we would need, what trajectories to prepare for, and how quickly such systems can evolve under the influence of a star. The fact that JWST, one of our most advanced observatories, is providing early data on this visitor underscores the point. Space science must be adaptive, reactive, ready for oddballs. The trajectory change of 3I Atlas suggests that we cannot rely on only conventional expectations. In sum, 3I Atlas is shaping up to be far more than a curiosity. Its unexpected behavior, its origin beyond our solar system, its shift in course toward the inner solar system, all combine to make this event deeply significant. If it completes the journey and comes near Earth's orbital path, our opportunities to study it will be unmatched. To probe alien solar system chemistry, to understand how an object reacts to intense solar heating from an outside trajectory, to test our models of object detection, tracking, and planetary defense. Even if it does not strike Earth, the fact that it may come close enough to offer rich observational opportunities means we're effectively witnessing a cosmic messenger from another star, passing through our neighborhood, one whose path is no longer simply predictable, and whose implications extend into how we think of Earth's place in the galaxy. Astronomy isn't just about distant stars, it's about our vantage in the cosmos, and 3I Atlas is knocking at the door, reminding us how interconnected our system might truly be, how vulnerable and how privileged. The sun has drawn this visitor close, and we are watching. There's more to unravel about the journey of the interstellar object, 3I Atlas, its evolving behavior, the deepening scientific intrigue, and the ripple of questions it sends through our understanding of planetary science, astrophysics, and even the boundaries of Earth's cosmic neighborhood. The telescope networks and space observatories pursuing it are now racing not only to track its position, but to decode the many layers of what it means, where it came from, how it formed, how it reacts to our sun's environment, and how, with the latest observations, its course appears more mutable than many had assumed. When 3I Atlas was first detected by the Asteroid Terrestrial Impact Last Alert System in July of 2025, the excitement stemmed from its interstellar origin. It was only the third confirmed visitor from beyond our solar system. Early orbit modeling showed a hyperbolic trajectory and remarkable incoming velocity, at one point measured at more than 130,000 miles per hour, 209,000 km/h. That alone set it apart. But the unfolding story quickly revealed something even more compelling, that this object is not simply a visitor passing through on a fixed track, but is being dynamically altered, its trajectory changing, its activity ramping, its very identity shifting in the light of fresh data. One of the most striking features has been the nearly flat, nearly retrograde orbit of 3Y Atlas, a path inclined only a few degrees relative to the ecliptic plane, yet moving in the opposite direction of the planets. That retrograde movement enhances the likelihood of higher energy interactions with the solar system's environment, meaning its approach is more aggressive relative to the Sun's frame of reference. As it approached perihelion, its closest point to our Sun, about 1.4 AU away, its response to solar heating has become evident. What had drifted through interstellar space for eons, largely inert, is now awakening. Observations from the James Webb Space Telescope, JWST, and other advanced platforms showed the presence of an extended carbon dioxide-dominated coma around 3Y Atlas, a cloud of gas and dust that is unusually generous compared to many of the comets native to our solar system. The comet's makeup thus hints toward formation in an environment markedly different from ours, a colder, possibly more distant region around its parent star, with different volatiles frozen in. That difference underscores why its changing trajectory matters. The way it reacts to solar heating, outgassing, and gravitational influences is likely different from standard comets. What does trajectory change mean in this context? Consider that as 3I Atlas draws nearer, sublimation of ices, especially those abundant volatiles like CO2, begins to dominate. The resulting outgassing acts like tiny thrusters, altering the momentum of the body in subtle but measurable ways. Dust jets, gas plumes, anisotropic emission of material all combine to shift both its speed and direction. For an interstellar object that arrives fast, these non-gravitational forces may prove more significant than they do for many slower traditional comets. Moreover, its high velocity and retrograde orbit mean the solar radiation and particle environment it experiences as it plunges in are more extreme, increasing the potential for rapid changes in behavior. Scientific teams have already documented significant dust and gas emission patterns that deviate from standard expectations. For example, the coma size is expanding, dust patterns are unusual, and nickel vapor has been detected, an element not typically observed in such abundance in this setting at this distance. Observatories like the International Gemini Observatory and the Hubble Space Telescope have imaged the object in dense star fields, revealing that despite its tremendous size estimates between roughly 0.3 and 5.6 kilometers in nucleus diameter, the heart of the object remains elusive. All of this points to a body that, once nearly dormant in interstellar space, is now extremely active in our neighborhood, and that activity feeds back into its path. Herein lies the significance of the shift in its course. If 3I Atlas is responding dynamically to solar heating and particle flux, then the simple models of interstellar comet trajectories, as essentially ballistic, passive, and mostly unchanging, are inadequate. We are witnessing an object whose path is evolving in real time, with the possibility of being nudged into an orbit that brings it closer, or with a different exit angle than first predicted. In a larger sense, that means our mapping of future interstellar visitors, our prediction frameworks for their paths, and our calculations of potential encounters must adapt. From an astronomical observation standpoint, this is thrilling. Each new tweak in the orbit offers fresh data, fresh leverage to test our physical models. How much mass is lost as it nears the sun? What is the distribution of volatiles and dust? How much does jetting accelerate or decelerate it? If the trajectory diverges significantly from expectations, we gain insight into how interstellar objects evolve under the influence of a star they did not originally orbit. From a planetary science and solar system dynamics viewpoint, the encounter of 3Y Atlas is a natural experiment, a once-in-many-generations chance to watch an object formed elsewhere being processed by our sun's environment. It deepens questions. How many such wanderers transit our system unobserved? What is their cumulative contribution to the mass, dust, and ice inventory of the solar system over eons? How might such objects carry alien compositions into the solar system, and how do they interact dynamically with our planets, asteroids, dust belts, and solar wind? Near Earth, the implications are subtle but real. While current modeling indicates that 3I Atlas does not pose an immediate collision risk with Earth, its closest approach is still on the order of more than 1 AU at present estimates. What stands out is how rapidly things can change when a body is under dynamic forces. The lesson is that interstellar visitors may require a different hazard monitoring mindset, one where we assume more than just straight-line ballistic behavior and account for outgassing, fragmentation, radiation pressure, and other wildcards. In the event of an object whose origin lies beyond the solar system, the surprises may outnumber the certainties. There is also the broader question of compositional exchange. Rather than just passively observing, we may have the chance to sample, via remote sensing, the pristine materials from another star system. In this case, 3I Atlas carries with it not only the record of its formation, but the entire history of deep interstellar travel. Radiation exposure, collisions with dust, cosmic ray bombardment. Its outer layers may be heavily processed. Studies suggest that its surface may carry an irradiation crust, a relic of billions of years in space beyond the solar system. The moment it enters the warmer sun sphere, that crust may crack. Sublimation sets in, exposing fresher layers, altering albedo and behavior, factors that feed into both its physical appearance and its trajectory. In observing 3I Atlas now, scientists are effectively watching a transformation in progress. It is not simply passing by, it is being remade. The blurring of boundaries between visitor and active object is fascinating. Its fate after perihelion will be telling. Will it survive intact? Will it fragment? Will it change its spin or release large chunks of material? Each outcome is a data point on how interstellar comets behave when subjected to a solar system's inner heat and gravitational milieu. Another dimension of this object's story is its journey and origin. While we may never trace it back to a specific star, models suggest that 3Y Atlas may be billions of years old, potentially older than our solar system itself. The fact that such ancient pieces of another system can visit ours means that the exchange between star systems is not purely theoretical. It is happening, albeit rarely and quietly. The matter, dust, and ice budgets of multiple systems can and do spill across interstellar space. 3I Atlas is a messenger of that process, now accelerating and shifting course under the influence of our star. Given how quickly the object's tail, coma, and activity are evolving, the real-time aspect becomes crucial. For example, infrared spectroscopy from Webb and other instruments is revealing changing abundances of volatiles as it warms. The presence of nickel vapor and the unusual dust patterns noted suggest mineralogical makeup worth of study. These are not static features. As the comet approaches and then recedes, the diagnostic signatures will evolve. That means the mission to understand it is time-sensitive. Each new measurement changes the baseline. Are we seeing primordial ice? Or material altered by billions of years of cosmic rays? Are jets pushing mass in unexpected directions? Is the nucleus stable? Or is it shedding mass at a rate that will change its center of mass and thus its orbit? In thinking about implications for future interstellar object ISO encounters, 3I Atlas might redefine how we prepare. Historically, many planetary defense programs assume solar system origin objects with more predictable behaviors. But an ISO like 3Y Atlas demands flexibility, early detection, rapid follow-up, multi-wavelength observations, responsive trajectory modeling that includes non-gravitational forces. If its course is being altered by its own outgassing, by solar radiation pressure, by dust mass loss, then predictions based purely on gravity will be inadequate. The increased inclination to plan for dynamic responses is a direct outcome. On a philosophical level, the appearance of 3I Atlas and its shifting path prompt reflection on Earth's place in the galaxy. Our solar system might not be as closed off as once thought. The boundaries are permeable. Objects formed elsewhere, carrying foreign compositions and physical histories, are passing through. If we can detect and track them while they are still active, we expand our field of view. Not just geographically using Earth-based telescopes, but temporally, looking backward into other systems' formation epochs and forward into how such objects behave. That broad view challenges the isolated solar system model in favor of a more interconnected cosmos. Another facet worth considering is how 3I Atlas interacts with the solar wind and magnetosphere environment as it moves inward. Its high-speed retrograde orbit and active outgassing mean that the physics of its interaction, magnetic draping, ion tail formation, dust plasma coupling, may differ significantly from typical solar system comets. Early data shows the coma is already extensive, and as 3I Atlas crosses regions of higher solar particle flux, its material may be stripped or shaped in unusual ways. That interaction could reveal not just the nature of the object, but the nature of the solar system's traffic lane for interstellar visitors. As its nearest approaches to planetary bodies occur, even if not imminently Earth-crossing, we must treat the event as a test case. For Mars, Venus, and Jupiter, the flyby distances are non-trivial. Some spacecraft may get serendipitous opportunities to sample its tail environment. Instruments aboard Mars orbiters may detect dust or plasma from 3Y Atlas when it skirts by. That matters because if a spacecraft sitting in Mars orbit picks up a faint burst of interstellar origin material, we gain a precedent for interplanetary detection of ISO encountered material. Such cross-planet spacecraft events feed into how we design future missions. Not just flyby of asteroid, but opportunistic ISO tail interaction. Returning to the path toward Earth, while current modeling suggests a safe distance, what is most compelling is that the evolving trajectory might bring it closer than expected, or alter its exit route such that it remains in the inner solar system longer or pass differently than earlier calculations. The possibility of that forces us to keep monitoring, to refine our error bars, and to factor in the non-linear behavior of an active body responding to heat, radiation, and mass loss. The margin of safety is real, but a non-zero unknown remains. Observers around the world now point to 3I Atlas not as a passing curiosity, but as a milestone event. Its brightness is increasing, its tail is growing, its activity is ramping. The time window for optimal observation is narrowing. By the time it recedes again into the outer solar system, the story it carries, composition, dynamics, history, may fade beyond our reach. The urgency to capture as much data as possible is high. Amateur astronomer observers, professional networks, spacecraft data links are all being coordinated to follow every shift. In practical terms, we are witnessing the deepening moment of what if. What if 3I Atlas fragments? What if its mass loss accelerates so much that its trajectory changes significantly? What if its composition reveals something alien, chemistry or mineralogy unlike anything in our solar system records? These questions have real answers in waiting, and the event unfolding now is the laboratory. The implications of what we find might ripple into models of planetary system formation, into our understanding of the galactic environment, into how solar systems exchange material, and perhaps into how we think about the origins of life. To bring the cosmic scale closer to home, Earth is a small planet in a galaxy filled with stars, nebulae, and countless bodies. The arrival of 3I Atlas, with its changed course and deep origin, reminds us that we are not isolated from the galaxy's flows. Our solar system is a conduit, capable of capturing, transforming, and ejecting material. 3I Atlas is doing just that, coming in, being reshaped by our star, and then likely exiting, altered with a new story to tell. We are fortunate to observe, perhaps for the first time in human history, an interstellar object with enough data collected and enough activity to permit the tracking of its evolution through the solar system. From the perspective of human knowledge, the event acts as a bridge. On one side, we have our established knowledge of solar system comets and asteroids. On the other, we have the unknown of extrasolar wanderers. The boggling part is how little of our textbooks had prepared us for an interstellar object that actively alters its own path in the inner solar system in real time. The result compels us to update our models, to collect more data, to ask sharper questions. In the months to come, as 3I Atlas continues outward, or if its path brings it to nearer vantage points, observations will yield not just one dataset, but a time series of change. How its coma expands, how its emission rates evolve, how dust jets form and dissipate, how the nucleus cools and loses mass. All of these feed into an evolving profile. That profile is rare and precious. If it behaves differently than expectations, the difference becomes as instructive as the match. It is impossible to forecast yet the long-term itinerary of 3I Atlas with precision. Will it swing out and leave the solar system entirely? Will it become gravitationally captured into a far outer orbit? Will its mass loss budget reduce it to a rubble pile that then fragments and scatters? Each path has distinct consequences. If captured or slowed by interactions, the interplay with planets, dust belts, and solar wind might linger. If ejected, we still get the record of what happened under sunfall. The continuing trajectory change means we must remain vigilant, adaptive, and open to surprises. There is a cultural and human dimension. When people look up and learn that a visitor from another star system is moving through our solar system, changing course, being tracked, is observed, that ignites public imagination. The combination of cutting-edge science, cosmic scale, and the unknown has that rare mix of awe and relevance. The fact that we might, in real time, simply observe and learn and respond to something coming from the galaxy at large is a statement about what humanity has achieved in astronomy and what remains to be done. In sum, the evolving story of 3I Atlas is one of unfolding revelation, a body from beyond, arriving at speed, reacting to our star, changing its path, carrying ancient chemistry, challenging our models, and doing all of it in our observational reach. The trajectories we model today may shift tomorrow. The data we collect will refine our understanding, and the implications of how that object behaves will echo into how we approach the next visitor. The cosmos is less predictable than we sometimes assume, and 3I Atlas is driving that lesson home in the most visible way yet. As 3I Atlas continues its steady glide through the solar system, a deeper understanding of its evolving behavior begins to take shape. Each new image from the James Webb Space Telescope reveals a slightly altered structure, faint variations in brightness, subtle distortions in its coma, and ripples in the tail that suggest powerful internal and external forces are in play. Astronomers monitoring its course describe it as a living system in motion, sculpted by light, heat, and time. The object's changing trajectory underscores the fact that the universe remains in constant flux. Even something that has drifted between the stars for billions of years is still vulnerable to the gentle yet inexorable hand of solar influence. The JWST's infrared observations have been especially revelatory, capturing signatures of exotic compounds in the comet's vaporizing shell. Scientists suspect that beneath the irradiated crust lies a core of pristine material untouched since the birth of its home system. The ratios of carbon-bearing molecules are higher than any comet seen before, hinting at an origin in a colder, dimmer stellar nursery than our own. These findings imply that 3I Atlas may be a relic from a system with a faint red or orange dwarf, a place where sunlight was so weak that carbon dioxide, methane, and nitrogen ices condensed freely. The exposure to our sun's radiation now forces those ancient ices to erupt in spectacular jets that propel it unpredictably, subtly reshaping its orbit and giving the impression that it is steering itself through our cosmic backyard. The fact that the object appears to be veering toward the inner solar system opens a window for extraordinary research. Ground-based observatories in Chile, Hawaii, and the Canary Islands are coordinating with JWST and ESA's Gaia mission to triangulate precise measurements of its shifting position. Radar specialists are preparing to bounce signals off its surface if it approaches within range, potentially allowing the first ever direct mapping of an interstellar nucleus. If successful, the data could refine models of how interstellar bodies respond to stellar heating, radiation pressure, and gravitational tides, all of which are acting simultaneously on 3Y Atlas in ways never before observed. At the same time, theorists are considering what its movement tells us about the galaxy's population of nomadic debris. The Milky Way could be filled with countless fragments like 3I Atlas, silent drifters ejected during the chaotic early years of star formation. Some of these may eventually find their way into other systems, just as this one has. The implication is that cosmic exchange is far more common than previously believed, a steady circulation of matter that blurs the lines between one star's domain and another's. Earth itself may owe part of its own composition to such exchanges, seeded long ago by ancient interstellar wanderers delivering complex carbon compounds to the primordial disk that became our home. Every telescope aimed at 3I Atlas right now is not merely studying a comet, but watching a story unfold. One that bridges systems, epochs, and the very boundaries of what we consider local. Its shifting path reminds us that the universe is an open system, endlessly exchanging material and energy across the void. Whether or not it draws closer to Earth, its presence affirms something profound. We live in a galaxy of travelers, and sometimes those travelers come close enough for us to witness the light of their long journey breaking into our sky. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on 3I Atlas changing course toward Earth? We want to hear from you. Thank you for watching, and see you next time.